All right, I think we're going to get started. Just in case this is a room check, this is the DNS track. We've got 3 talks on various things relating to the DNS and some of the ITF efforts, some of the security issues that are going on. First up is going to be Tim Wasinski. He works at Salesforce and is also the co-chair at the IETF in the DNS Op Working Group. And he's going to sort of go through some of the initiatives that are going on right now in the DNS Op group relating to DNS and privacy.
Oh, we actually have
You have a dongle, which, yeah, make sure this resolution works.
I have to do this. That's what I was doing. Actually, it doesn't show. No, I don't see it picking it up. I'll try mine. That was the thing I didn't do. So this one worked in Toronto, so I feel confident that we're in good shape. Or else it's technology itself. Whoa. Well, we have a total failure. So no. Where is our gentleman? I guess we're not going to start right now.
Yeah.
We failed to test the technology.
Power cycle it? Sure. So I'll need to go back in. Yeah.
No, I could. Yeah. Try yours.
There we go.
There you go. You plugged it and plugged it back in. Yay. Technology. There we go. So, all right, good afternoon. I'm Tim Wasinski, as he had said, and I probably, if you guys have go to IETF, we've probably talked in the past. Like I said, I co-chair DNS operations at IETF, which has a lot of various work going on, but this is more work on sort of the DNS privacy sort of problem, sort of the problem space, which is sort of definitely not operations and more of a, say, application type issue kind of thing. So what is the problem here? You know, in being network people, you've all seen the TCP dump data. You know, we're all used to sort of snooping at people's traffic. That's Warren's TCP dump data. So if you want to go figure out what he's up to, he's very willing to sort of share that. So in the big picture, you know, you're some end user sitting in a hotel conference, you know, using the Wi-Fi or a coffee shop or something like that. And there's no expectation of privacy with anything, especially your DNS queries. And the major thing is they don't know what sort of data they're leaking out there. People just aren't paying attention. And so they easily can be sort of, as you can see, you can sort of easily see what's going on in some sense. And, you know, networks are compromised. Networks and servers, everything's compromised nowadays. You know, it's not a matter of if, but when. You can't assume that, you know, what you have out there is secure on any sort of level. Also, with the IETF, they have sort of taken the approach of pervasive monitoring as an attack. They view it as an attack vector, much like anything else. And they're actually going back and sort of focusing more on privacy in terms of in all the protocols in light of, I say not just recent revelations, but just in general. They're sort of taking a new, closer look at making sure that the things that exist out there, the protocols that exist, have an ability to sort of give people some sort of privacy of what's going on. And it's not always encryption, right? I always try to make the distinction privacy, confidentiality versus just sort of encrypting the solution. But if you look at it in the small picture, DNS queries leak metadata. If your query is not cached, your entire query is passed all the way up the route for people to sort of poke at and prod at. And what you're seeing now is that's not very interesting. People may not think in a sort of simple view, it's not very interesting, but that can be aggregated by individuals or groups, and computers are really good at aggregating that data. And if you aggregate enough data over time, you can get an excellent view of what users are doing. And so that's something that it's worrisome to some. It may not be worrisome to all. But if you're looking at sort of conventional security, your sort of typical service hardening, does it help? Yeah, kind of, right? You take out the server, protecting your recursive servers from being compromised, but those servers, people are using public DNS servers all the time now, the OpenDNS, the Google, 8.8, they probably do a large number of queries. I know when talking with the OpenDNS guys at IETF, the number of sort of the volume of queries that they sort of take on every day is sort of, massive sort of thing. And it's like a nice exponentially scaling graph. So I think Warren had sort of 1% of the servers do 90% of the queries. Was that the 1% of the recursive servers out there do like 90% of the DNS queries on the internet? So that's sort of a small number of people sort of have a large view into that data, and that data is being mined, right? We all know that. And so even if you protect your servers, that data is still leaking. And that's not your fault, right? That's not anyone's fault, because that's the way the protocol is currently, is being implemented today. That the way the query names are passed around, the way that when you can look at stuff all the way up the stack, those queries are being, the whole query is being sent out. So when I looked at this, people always say, well, DNSSEC should solve this. I'm just like, no, it doesn't solve this. DNSSEC signs zones and allows you to authenticate the DNS data you have. I've got this data, it's valid, it's correct. It gives you some sense of data integrity. And it's good for the best thing it does is preventing man-in-the-middle attacks, which are really important. The next thing is everybody talks about is, what about DANE? And DANE's the DNS-based authentication of named entities, because when they see DNS and they see certificates, people say, well, that solves all the problems. And it really doesn't. It allows your certificates to be bound to DNS names, and it requires DNSSEC, and you can store those keys in DNS. But that only certifies that your certificate is valid and that your certificate authority has not been compromised, because people actually started to realize that, whoa, those can be compromised too. So DANE sort of solves that problem. So those solutions authenticate the DNS data, but your queries are still, there's still query data floating out there that just sort of being out there in plain text. And two ways to probably look at the problem is we can leak less data, or we can hide that data from malicious third parties or attackers or whoever wants that data, sort of thing. So you sort of view it from those two possible solutions. If we leak less data, one possibility is being discussed is sort of QNAME minimization, which is a thing of actually not actually sending the entire query string up the resolver chain. We're still unclear if that's going to actually, how much that's going to help. It's something that I think in DNSOP we're actually going to start digging into very heavily. There's a RFC on it, and I think it was NSD had actually, the NSD name server had actually started looking at some of that. Maybe it's the unbound version. But it's still unclear, like, even if you do that, where are the wins, right? Does it actually help? So I think people are going to try that, and we're going to see where that actually helps us or not. Then you sort of say, well, we can encrypt more stuff. but you don't, it's DNS, right? You can't encrypt a lot of stuff because it's an underlying infrastructure. We can't alter that without causing major pain everywhere. That it's just too many moving parts. So we're thinking of it as the HTTP to HTTPS problem, right? Back in the mid-90s. They had to put security on there. It was kind of ugly, but it worked for the time being. And, 20 years later, they're spinning the protocol again, right? So it's taken them 20 years to go from 1.0 to 2.0. So, it's not a trivial problem. And we're in sort of doing this research and kind of looking at the problem space. We're looking at focusing on the communication between the stub client and recursive resolver, right? The stub client could be something you're running on your machine, DNS mask, you can be running, any of those sort of things. That's closest to the end user. It's also the most visible, right? So it's the most obvious what's going on there. And it gives you a building block, gives us a building block to sort of leverage continuing. We looked at, to think about, we want to encrypt everything back to the authoritative servers. We started looking at all this sort of problem space, and it's a massive problem space, right? So to just say you're going to sort of tackle all of it is just crazy. So it just, we figure we can build blocks of it, and sort of, what came up in the talks was it's just turtles all the way down, right? You just keep stacking those blocks up, and eventually you may get to the root servers. But we didn't even want to talk about the root servers because there's all that other political stuff about that. So Warren and myself sat down and wrote a charter statement for what they're calling DNS Private Exchange. That's for a new working group that we're looking to have being proposed. And it looks like we're going to have something going on in the next one in November in Honolulu. We're trying to address these issues without overreaching the problem space. And so Warren and myself are starting off as co-chairs, and we're looking at developing deployable solutions. We want something that we think will work, right? Because you can get into this and you can just go down rabbit holes, and we can, I've been tracking the HTTP 2.0 stuff, and it's been a long road for them. So, of course, you can have a working group without a problem statement. And Stéphane Borzheimer of FRNIC out of France has put together a really good problem statement identifying a lot of the places where information can be leaked and things can be compromised, and we're using that as sort of the basis of where we're going to go, focusing on encrypting the conversations between client and recursive resolvers. And currently, there's actually two different proposals. One is the one that actually the folks from VeriSign are going to talk about next. It's the start TLS for DNS. They're flipping a bit. They're flipping one of the DNS option bits to actually start a TLS conversation in your DNS query. Did I get that right? Yeah, it's okay. It's like, yeah. So that's and that their stuff is very interesting actually. I find it very, very interesting what's going on there. And the second one is one that people are sort of throwing around by saying, let's just put TLS on port 443 and then just run DNS on top of that. And if it's ALPN, you can do it with running HTTP at the same time. And that also seems just very strange in its own way. But we all know that port 443 can get through pretty much all the firewalls. That's always the problem when you're looking at stuff like this. It's like you can't spin the protocol and open up a new port because every middleware box in the world is just going to break. So you have to figure out how we're going to address that. And people keep going back to that HTTPS thing of saying that seems it's so enticing, I think, is the way they view it. It's so easy. We can just do something on port 443 and run TLS on it, and everything's going to be good. But what I'm avidly not trying to work on in the working group is we're not trying to do DNS 2.0. I mean, that's just madness. And that's, it's a task of, that there's no good can come from that. So I'm focusing on like the integrity and the confidentiality of the DNS mechanisms, not trying to get into all the encryption stuff, though there will be some in there, but that's not the sort of the focus. We don't want to build some technically perfect solution that's going to take us, decades to deploy. Look, I mean, the install base in itself, between, just not between just servers themselves, but the middleware boxes and all the just the stuff out there that just, that sort of passed UDP 53 and TCP 53, to touch all that is a monumental sort of thing. But since this is a new working group, I think we're going to need, we're definitely looking for volunteers, people to help engage with the IETF process. Discussions have been going underway. There's been a DNS privacy mailing list where a lot of this stuff's been going on, probably for the past 6 months. We had a initial session back in February, I think, where a lot of this stuff was starting to flesh out, and we were able to separate what I call like the TLS encryption stuff from just the real, let's figure out how to sort of clean up what's going on inside DNS right now. What we have a session planned for Honolulu. It's a BOF. They actually tell us they figure it's going to be a real working group by then, and I'm very surprised because we wrote some charter text that made sense. We sort of said we're not going to do certain things, and so far everybody's like, yeah, that's good. You're not going to do too much. That's good. That's great. Let's go ahead and do this. But we will always need operator and vendor participation, of course, right? We have to sort of gather data and see, especially with the QNAME minimization thing or something like that, or tells what's going to break when we start turning stuff on, right? When we start tweaking with this stuff, where are the edge cases? Where is that? The law of unintended consequences, chases me every day. So that's the thing that I'm always like, and I know that some of the vendors have already started looking at some of this stuff. And so it'd be good to sort of start collating that sort of information. But that's kind of where we've been. And I know the VeriSign stuff is really it's going to dig more into their TDNS thing, but I know we have time because Paul said somebody had bailed. So if there's any sort of questions out there.
Hi, John Christoph from Team Cumry. I know this has come up before, this question, but I hope if you'll just allow me to ask it again here and you could address it. So I know there's a real reluctance to embrace Dan Bernstein in the IETF, and I think the feeling is probably mutual. What's the
you mean with the curve?
Yeah, what's the reason for excluding curves? I know there's certainly.
There's actually no reason for excluding curves, and actually curves has been like part of the big discussion when we first started having the encryption discussion, and I think I think there's not a solid feeling, like there's not a solid base of people actually using DNS curve in a way to actually see, can we get, what's the data look like, right? Does it actually work? How is it helping, sort of thing?
Okay.
So, and
if open DNS people here, it'd be interesting just to hear their take on it.
Yeah. So,
and actually, if I can jump in as well, I don't think it's quite universal that folks at the IETF dismiss the curve. There is some misunderstanding on some parts of what part of the whole transaction it secures. So I think some education on DNS curve solves a part of the problem very well. DNSSEC solves a different part of the problem very well. We actually, as engineers, usually sort of figure out the problem, figure out all the tools we have, and figure out which combination sucks least. And I think that curve is going to be part of that.
Yeah, and I personally, as sort of DNS Lab co-chair for the past year or so, I don't have that sort of bias. I know I know it quite well. I know everything that goes on there, but I don't sort of have that reluctance to sort of embrace something like that, right? And actually, we've been looking for folks that have actually been using the DNS curve stuff and seeing if we can get some operational feedback from them. So. Yep.
Yes. So Warren.
Warren said that Dan Bernstein showed up recently at one of the ITFs, and I know there was a lot of acrimony, probably about 10 years ago or so, about a lot of that. So I think that has faded with time. So.
Other questions?
So pretty quiet. So I know most of the usual suspects, right? The folks from VeriSign are here, and there's stuff on TLS. I think that is that what you're doing, TDNS? Yep. I find this stuff very fascinating, and so I think it's, so.
Yeah, so Glenn Wiley with VeriSign. So what you're thinking of, Tim, the TDNS work is part of a stub resolver initiative that VeriSign's working on. What Eric and I will talk about is kind of fundamental to that.
Okay.
It would precede that. But one of the things I'd encourage some discussion about you know, when you think of DNS, most of us, especially when we put on our operator's hat, we're thinking about UDP.
Yes.
And what that looks like on our platforms and networks in UDP. And there's some obvious implications when you start talking about moving to TLS. You know, what does that do to a typical DNS session? And as an operator, it's very interesting to me because they look nothing alike when I make that transition.
That's right. And a lot of that starts to fall back towards TCP, and that makes people concerned because there's a lot of state information, right? And I know inside DNS Opera, there's actually been some very interesting work going on with doing like TCP keep alives in DNS sessions. Paul Wouters from Red Hat has done some great, really work on DNS keep alives and chaining queries together. So for like DNS sec, where you actually have to do multiple queries in a row, he's got something where you can set the session up and you can keep that DNS query session open as a TCP session, make multiple queries against the server, and then shut it down when you're done. You know, like much like a regular like web, you know, HTTP sort of like a regular, you know, connection sort of thing. So, but the problem is it's not, you know, people just say UDP is great because there's, you know, it's like one less set of handshakes, you know, you don't have that SYNAC thing, everything's, you know, so, you know, and you probably, you know, if you track the HTTP 2.0 stuff, right, the speedy work, that they're all trying to get rid of those SYNACs and then, you know, to get more like UDP, and then DNS is actually starting to slide towards the TCP land because they need that extra sort of state information or that sort of session. That is true.
Yeah, so I you know, in past life, running very busy TLD authoritative servers, the thought of TCP, my initial reaction is kind of panic. I mean, you know, I look at that and think about what that does to the platform. But I think any transition, any large-scale transitions in internet infrastructure, that's a pretty normal response to these kind of transitions, and we just need to lead them with conversation and figure out what's coming.
I think
right?
you study the data, right? You look at the data, you figure out how things perform, and then where can you make, you know, improvements in that sort of thing.
Yep.
So, and yeah, and I apologize. I've been your boss has been sort of hammering on me about the TLS stuff, which is why I think I have it on my brain sort of thing.
I believe it. Yeah.
Yeah.
it's-
So and I you know.
busy.
So.
Warren?
Hey, Warren, co-chair with Tim. One of the other things to keep in mind about scaling is we're mainly discussing this for recursive servers, so stub to recursive, and recursives have very different scaling properties. Like they don't get separate really short connections from a lot of different people. They get separate longer connections from a lot of different people. So the scaling's not quite as scary as, you know, trying to do this for .com or large TLD. Okay.
Other questions? Okay, so next up we have Glenn Wiley and Eric Osterweil from VeriSign, and they're going to be talking about some of the things that we are doing with DNSSEC and DANE.
I was thinking it was more like it would have been a good 1-2.
Yeah.
Yeah.
We can talk to less.
Good. So I'm Glenn Wiley. I've been I spent about 7 years as the lead architect, systems architect at VeriSign for the ComNet name servers, and recently I've moved into an innovation group within VeriSign, kind of it's like a think tank, an incubator of ideas, things we want to change at the company, but at big companies that can be hard to do. So we created a small group that we can work in that has fewer of the encumbrances that come with large organizations. And Eric's going to be speaking with me too. He's seated because he was over enthusiastic last night, right? So, did you need a white Russian? What was the?
No, not
So, Eric's a principal scientist at VeriSign and VeriSign Labs. Did you want me to make a comment about that?
No.
Oh, I love it. I have top secret information on the slides here.
Redacted. Yes, redacted.
Yeah, yeah. So DNSSEC. So you think of a global distributed database, that's DNS, but DNSSEC is simply authenticated. We're going to talk about DNSSEC and DANE to try and drive some awareness here for folks that don't know. If you're already a DNSSEC expert and you're running assigned zones, then you can contribute to the conversation, but this won't be informative to you. It was originally about protecting against cache poisoning, man-in-the-middle attacks against DNS. And I think DNSSEC solves that problem very well. You could argue prior to that, there wasn't really any security to speak of, at least on the resolution side for DNS. But we can take that a lot further, and we'd like to talk about some of the things you can do with DNSSEC. RFC 3833 enumerated some of the attacks against DNS. Everybody knows what they look like. They know what you can do with these things. But one way to think about it is if I posed a question, some meaningful question to somebody I know in the audience, I ask Schumann something specific, and then Warren decides to give me an answer, why should I trust Warren if I don't know him? But that's exactly the problem you have with DNS. Should I trust Warren if I know him?
Never trust Warren.
Never trust Warren.
So, when you look at DNS, that's really what's happening. You're throwing a question out there, and you get an answer back that you hope is from the person that you asked, but you really don't have any guarantee that that's actually what you're going to get. So we've done things over the years to try and tune this up a little bit, but DNSSEC provides a positive solution to that question. And DNSSEC finally has a killer app. So you think of infrastructure security. That can be hard to sell when you talk about armoring channels or creating security behind the scenes that people can't see any evidence of on their desktop. It can be hard to sell folks to spend money and time to implement it. Dane is that thing that brings DNSSEC to the point where folks actually have a reason to use it. They see that they have a reason to use it, rather. It lets them see manifestations in applications. Eric's going to talk about secure email, TLS. There are lots of ways you can actually leverage DNSSEC to do something even more interesting than just guaranteeing that you got an answer from the person you thought you were talking to. It's exciting to me because it's actually operational. We've seen adoption is slow. In .com, I think we're at between 300 and 400,000 zones out of our, 110 million zones under COM. So that's a low adoption rate, but it's moving forward. In 2013, I saw one study that said that 8% of the queries were validating. August of 2014, 12% of the queries in North America are validating. So that's a nice, the curve is looking better. It's moving forward. The point, though, is it's real. It's actually out there. It's on the networks, and people are using it. It's not hypothetical. Now, hopefully this isn't going to be informative to anybody in here, but we'll take one slide just to refresh your memory about how DNS works. And that is, it's hierarchical. Authority is distributed down this hierarchy. It starts with the root server, the dot, and then moves to a TLD, say .com, to a third level domain. And you can have iterative queries. So the idea, if I want to find example.com, I'm going to ask the root to find me a COM name server, and then I'll ask the COM name server to find me an example.com name server, and then I might ask example.com to give me a host name if that's what I'm trying to get to. But the idea is that I iterate over that tree. Iterative name servers, recursive name servers can do this for me, so I can just ask a recursive name server, give me a host IP address for example.com, and it goes off and does all that work, or I could do that locally on my resolver on my local machine. So when you look at how DNSSEC changes this, I'd point out a couple of things. This is, by some standards, our first attempt to deploy an internet-scale crypto system. The DNSSEC zones employ public and private keys, which is something, if asymmetric cryptography doesn't work, we have a lot of more serious problems than DNS. We sign all of the pieces of the zone, and then the resolvers are configured to take advantage of this. So you start off with a root key, a trust anchor that you would get from IANA. And as you issue queries, you'll go get the next key from root, and then from COM, and then you can go down to your final destination. And as you accumulate these keys, you're building a chain of trust through signatures that lets you know for a fact that where you finally ended up is legitimate. Eric, you want to take this bit?
So this is, a lot of this so far has been meant to sort of just, re-bootstrap all of us on, to sort of what Tim was pointing out. What exactly is DNSSEC trying to do so that you know the negative, like what it's not trying to do? So, at a really simple view, so after the illustration that Glenn just showed, you see sort of climbing through a hierarchy and pulling a key back. But, at the low level, what that might look like is the following. So, here's an example of, an NS set for some random zone that we're familiar with, at least where we sit. And DNSSEC will take a crypto key, and that crypto key plus that NS set will just annotate with a bunch of gobbledygook at the bottom. The signature that lets you verify that things haven't changed in flight and that they come from where you thought they come from, or if they don't exist, you can prove it. And that's pretty much all it is. So DNSSEC, goes from a hierarchy to just some gobbledygook in our sets. And the gist of that really is just with one key on my resolver, we expect or we hope that you wind up being able to securely authenticate data that you get from wherever it comes from throughout the DNS hierarchy, whether it's the root, a TLD, the zone you're going to, whatever. So that's DNSSEC's job. It's not to hide things, it's not to encrypt things, it's not to protect your privacy. It's to make sure that when you ask a question to Schumann, you know that it was Warren who answered you. Whether or not you trust him is your own business. So dovetailing that back to what Glenn teased, so DNSSEC has got this thing that we think is a killer app. It's called Dane. And there's a handful of people in the room that I know are very familiar with this. But, I want to kind of go over it at a really high level because it's really brain dead simple. And that's, I think, one of the features. And some people started off by looking at what can you do with DNSSEC to help aid TLS? How can you help TLS, which is a fully robust, mature protocol that we use all over the place, but how can you help it do a little bit better? And as Glenn mentioned, DNSSEC is built on this notion of, I want to build a chain of trust. I want to give you one key for the DNS root, the DNSSEC key for the root, and I want that to chain down to wherever you go in DNS. And what Dane says is, well, when you get where you're going, why don't we extend that chain over to the next thing? So like when you get to a web server from www.example.com, can you get a link in the chain that says, since you could validate all the way down in the DNS world to www, why don't you also validate over to the key that comes over that TLS session? So to explain that, let me contrast it to what we do today. So there's a PKI, a web PKI system that we use for HTTPS. And what that basically is a whole bunch of certification authorities that all can attest to anything that they want. And how you get that list is not standardized, and it's not visible to most users. You basically your machines and your browsers are born with a whole bunch of keys. You hope that they're kept up to date, and any one of those keys associated with a certification authority can tell you whether or not you've gone to a website and the key matches that website. So what that basically means is, like it says at the bottom, there's a weakest link problem. And so there's been a number of notorious attacks. DigiNotar was probably one of the first well-known ones, but definitely not the first and definitely not the last, where a rogue certification authority or a certification authority that had been compromised issued some certificates for domains that it shouldn't have because they didn't have a deal or because that domain had not purchased certificates from them. And those can be served with impunity, and no one can validate the difference because your browser, a relying party, gets a certificate and it says it's valid because one of these guys said so, and you don't even notice that, let alone can you figure out whether it's righteous or not.
Can I add, Eric?
Yep.
If you wonder whether that's really a problem, think about what you've seen actual users do. I know all you guys are security aware and you'd never do that kind of thing, but how many folks do you see click through the, hey, this server doesn't look like what it ought to look like. Do you want to accept or accept the exception? Who actually reads that if you're not aware of it? Like, all of us do. All of us do. But, right? So what Eric's mentioning, I mean, think about it. You see this all the time, especially if you're in a hurry trying to solve a problem. A challenge comes up for SSH. You get a host key. Oh, yeah, that's new. Okay, it must be the right machine because I just typed an address to it, right?
And that's assuming you even get that dialog box, because what's particularly pernicious here is that if I can compromise like a CA that's in I think it's a country CA, and I can have that mint a certificate for Google or for VeriSign, then your browser doesn't even warn you. It's like, yeah, it looks like it passed a check. It's good enough. So one of the things that Dane does is it says, well, why don't you have that domain authority actually tell you what you should expect on the other end of the channel? So one of the problems that TLS has with this approach is that you go over an untrusted channel, you go over TCP, and you get back something. You get back a certificate, and you expect that to be self-verifying. And the way you kind of made that all work is you had, you know, depending on how you count, 170 or maybe even thousands of different certificates that can verify it, and they're all managed separately and whatever. Dane says, well, you got to that IP address. DNSSEC helped you verify it if you used it, you should. But you got to that IP address. Why don't you ask the same authority that gave you that IP address, what sort of crypto information should you expect when you start a TLS session? You know, it's sort of like, it should seem obvious upon inspection or reflection. It's like, yeah, you know, if your DNS was compromised, you never got to that IP address. So you're obviously counting on people to get the proper data from DNS. And you can use DNSSEC to try and help with that. But while you're there, why don't you just find out what you should expect when you make this connection over an untrusted channel? So that's what Dane does. That's one of the things that Dane does. Actually, Dane does a lot more than that. So Dane, we've been talking about TLS, but Dane's actually kind of like a multi-tenant system. It's a multi-tenant system in the sense that you ought to be able to do this same sort of extension of the chain of trust for other keying protocols, whether that's, you know, for email, for VPNs, obviously for TLS, et cetera. And that's its sort of its goal, and that's what's being worked out now. So some of this is more baked than other parts of it, but that's the kind of the simple observation that Dane makes. So I'm going to kind of like fly through this, but I hope if somebody has questions or comments or they don't agree, you'll just jump up right away, because otherwise this will just be kind of boring. But Dane's basically trying to be kind of like this. Well, my interpretation of Dane, so we have like one of the co-chairs in the room, so I expect that he'll keep me honest. One of the things that you could look at is, I want to use this as an opportunity to learn keys securely for protocols that need them. So it uses DNS, and in the DNS sort of transaction chain, there's a couple places where there can be an adversary. It can be during the provisioning stage. A lot of people have claimed, oh, well, that's not a very secure approach because someone can, you know, go to my registrar and muck with my zone. It's like, yeah, then they never would have got your A record. You never would have, like, that IP address never would have got there. But that is a valid concern. So there's a point of vulnerability there. There's a point of vulnerability between recursive resolvers and authoritative name servers. There's a point of vulnerability between your stub resolver and the recursive resolver. At these points, there's adversaries in the network that could try and mess with you and blah, blah, blah. And Dane says, well, between DNSSEC and the extension of the chain of trust, it's going to try and protect you against all those. So you can just simply say, I've got a key that is associated with some secure whatever the heck. I'm going to put it somewhere. And then someone that you've never met before can say, I stumbled across your key and I'm going to use it now. And I'm just going to be able to trust that security was managed in the middle by using DNSSEC, by using Dane. I don't have to worry about, oh gosh, how do I learn your email key? Because, you know, how many signatures in the web of trust is sufficient, blah, blah, blah. You just say, I just use Dane, whatever that is. I can look in the protocol and I can look at the details, but this is supposed to be a utility that people can use. And so there's a number of discussions people are starting to bring up, specifically around SMIME, specifically around OpenPGP. There's some other ones about XMPP, IPsec, et cetera. A lot of protocols that are very mature, that have, you know, varying deployment bases, that may have reached difficulty in full internet scale deployment because of key learning problems. And so I think this is a little bit rot. So Dane's basically, one of the things that it does, wow, that was a lot louder, is it just sort of, I'm sort of like going to repeat myself here, it just sort of like extends the transaction chain from hop by hop. It sort of says, hey, the provisioning, if you can secure the provisioning, you can secure the channel between recursive and name server, then you don't have to worry about how you got that key. You just found it in DNS just like you found everything else. And that's kind of its simple observation. So, you know, it's so simple that it's too bad it took me so long to say all this, because really what it just says is, if DNSSEC is operational and deployed today, then why don't you just put your crypto keys in there? And if you have a protocol or a service that is using DNS domain names, then why don't you just let that same infrastructure offer the key learning, so you can go and bootstrap everything from SMIME to PGP to IPsec to TLS to whatever else. And one thing that's probably worth noting, and I want to say this really loudly, Dane does not obviate the need for CAs. It can, if you want, it doesn't have to. And I think we don't say this often enough. The Dane approach is actually very compatible with certification authorities. Certification authorities do something different than make sure that the domain name and the crypto key belong together. They do that. But they also say, I want to give you some notion of trust. I want to give you a little green bar that says you're at Bank of America, not Bonk of America, or something like that. And that's, if I go to Bonk of America, yeah, I went there. If I think that's the place where I have all my money, I'm wrong. Certification authorities try and help me figure out that last part. And Dane actually has protocol semantics to embrace that. So I am going to kick it back to Glenn now.
Yeah, so my background is development, so I have to put at least something that looks kind of like a function signature in every slide, every deck. But if you're used to doing, if you do any development, libc entry points for DNS are this. And you're not going to see DNSSEC related stuff, Dane related stuff in those libc entry points. My encouragement is that there are a lot of good alternatives to the traditional entry points. We've got, VeriSign's been involved with Internet Labs on GetDNS, which is based on libunbound. There are plenty of other language bindings that give you visibility into DNSSEC and the Dane bits that can actually make them work. You don't have to wait for somebody to build something. The stuff's already there. Signing a zone is really easy. And I'd love to say specific registrar names here, but I don't think I'm allowed to do that. So, but I'll tell you what, there are plenty of registrars that offer the means to sign your zones. They walk you through it. They give you, it's visual. You know, I know if pretty pictures irritate you, it's going to be irritating. There are other ways to do it. But if you don't want to learn, if you don't want to become a DNSSEC expert, there are plenty of registrars out there that will do it. If they're not supporting DNSSEC, ask them. So when I've talked to registrars, often the ones who don't support DNSSEC yet, the response is, well, we don't hear people calling for it yet.
The new GTLDs all have to support it out of the box.
Yeah, that's a requirement.
Yeah, comment being that all the new GTLDs have to do DNSSEC out of the box.
Yeah, that's great. So like I said, if your registrar doesn't support it, ask them to, and if they don't, find a better registrar. What you end up with is this lovely little DS record. That's the thing that ties everything together. You can create that along with your keys with one command. It's really not that hard. You can find much harder ways to do it. There are a number of documented mechanisms that take 6, 7 pages of fine typed commands. You can do that if you like it, if you don't want the pretty stuff. But the fact is, it's really not that hard. And I left out some other details. You have to move a few files around. But the bottom line is, signing your zones, it's not difficult. The other thing I'd add, one of the objections I've heard in the past is I'm putting too much trust in DNS. The DNS is taking on too much responsibility when we try and move to DNSSEC, start moving keys in here to do some of the stuff that Eric talked about. And my challenge to that is, you already trust the DNS kind of to an insane degree. I mean, when was the last time you verified even the IP address that you got back from a name lookup? You're, okay, wrong people to ask. So really, seriously though, people inherently trust the DNS tremendously. The idea of armoring it and using it to deliver keys for other things makes perfect sense.
Yeah, and just before we go to the question, I definitely want to get to that. I just want to underscore, I think one of the big points of the talk today was to say, a lot of us have probably heard of DNSSEC. How many people have heard of Dane before today? Awesome. So glad to see that many hands. And so, yeah, so hopefully we're preaching to the choir, but what we really wanted to do is get on record and say, DNSSEC is very, very doable. There's now a very clear reason to do it, and that clear reason is something that you could maybe even expect end users to push for. So suddenly there's a reason for people to say, why would I pay extra, or why would I go through the extra effort for DNSSEC? So that was really what we wanted to underscore, is a whole bunch of things that have sort of come together, and some operational pain for the last few years with DNSSEC that's may be about to pay off.
So, questions?
Brett Watson, Infoblox. Don't we still have a problem, and Eric, you touched on this when you first started chatting, when we have certificate authorities in our browsers that we have no way how to validate knowing whether they're good or bad, don't we still have a problem with bad certificates?
Well, so that's one of the things I really love about Dane, is that with Dane, you don't need those anymore if you don't want to use them. So Dane basically makes it unambiguous whether you got the cert that the domain holder wanted to serve you or not. Now, the certification authorities are still the place you would go in order to say, do I trust it? Do they have a CFO? Are they do they have an address? Is there a building there? And that's really useful. But it makes it unambiguous that this domain is bound to that key. And that right now, the certification authorities, they conflate those two goals together, and it kind of weakens the overall approach.
And I don't know if we made it clear, but the TLSA record allows for you to publish, I think we did put it in one of the slides, but it allows you to publish a key or a reference to a CA. So you can use either. If you feel better about what you're doing, put your own keys in there.
Yep.
Hi, a comment and a question. This is Jeff Houston from APNIC. Firstly, the comment. In North America, around 20% of the entire sort of population of the area uses and validates DNSSEC, which is brilliant. Oddly enough, the US is second bottom. Above that is Greenland at 66%, and there's a small rock just off Newfoundland which is owned by the French, Saint Pierre et Miquelon, and 99% of the 5 fishermen there use DNSSEC validation all the time. And so in the rankings, the US is only second bottom. It's still good, but it's not brilliant. The question, though, was actually more about Dane and bootstrapping and tying it into Tim's stuff about a secure relationship between me and my resolver. How do you see that bootstrap? I'm like, theoretically, I can embed some keys to use for TLS itself somewhere inside the DNS, and I can name my resolver with a name. So in some ways, if I have the root keys, I can bootstrap myself up. How do you envisage that working, or am I going way too fast?
So I don't think anyone has settled their thinking on this yet. But a couple of us have put together a draft that's floating around Dane that would do opportunistic keying for IPsec tunnels, whereby if you have the address, the IP address of your recursive resolver, then you either probably have it in private space or it's probably a public recursive resolver. And in either of those two cases, you probably have the management of that probably has access to the reverse zone. So you can do a reverse lookup, do full chain validation with a stub like getDNS that Glenn was talking about. And then you can say this IPsec key, now I will create an opportunistic IPsec tunnel. So yeah, that's some of the things.
Yeah, the point is if you're really hard-nosed about it, you don't have to trust the resolver beyond your machine. You can do the iteration locally and be very confident that it's sound.
Oh, I had a question on Dane. I know a lot of people raise their hands saying they know about it, but how many people have actually tried to deploy Dane in their DNS besides Warren? So, okay. So yeah, I think I think it's something people know, but that's what I've sort of run across. It's like, it's still like they haven't actually made that hurdle yet, right? They actually haven't signed zones either.
So if I could ask a semi-unfair question, how many people got a little bit of extra knowledge about Dane out of the talk today? I mean, a lot of people said they knew it, which is great, but I mean, was this informative and useful, even like a little bit? All right, that's good, because it's great that so many people knew what it was. It's really great if we can sort of like, spread like to point Tim's making. I mean, whether you've played with it or not, we really want people to understand it too, because sort of to the point, one of the points Tim made in his talk, understanding that DNSSEC is doing this job and not that job is really important too.
Michael Sinatra, ESNet. Just a reminder that when we implement new resource record types, it needs to be implemented by the IPAM people. And so those of us who would love to deploy Dane right now can't always do it because either our IPAM doesn't support it, it might be on the roadmap, we hope it is, or we haven't upgraded yet and we need to find time to do that to the latest version of our IPAM. So that would be the reason that actually the former reason is the reason that I haven't yet done it. So that's sort of where we're stuck. In my personal vanity domains, yeah, I can play around with all I want, but for those who have IPAMs.
We're all bound by vendors.
Yeah, and so we need to push on that too. That's just one more thing.
I think that's a really good point. And I guess one of the hopes I think we have is that as Dane starts to make, because Dane is kind of like an eyeball focused kind of service. You know, you want like secure email, and that's a user thing. You want, you know, TLS and browser, maybe that's a user thing. That hopefully that helps us add more pressure for adoption. But yeah, it's just like a hope.
Yeah, and I want to meet some of those fishermen that are validating queries. I love that.
I'm wondering what the missing 1% of those 5 fishermen is.
Yeah. No doubt. Okay.
Any other questions?
Great.
Okay, then our last talk is with Dave Levin from the University of Maryland, and he's going to be talking about deroute and address change. So we will have our usual little audio-visual shuffle.
Let's open. That's pretty easy. Okay, hey folks, my name's Dave Levin from the University of Maryland. And for those of you who don't know, the University of Maryland has always hosted the D-root name server. And early last year, it changed its IP address. This is a pretty historic event. And so what I'm going to present is some measurement studies that we did that explain some of the phenomena surrounding this, unfortunately, probably last in a lifetime event. So just as a quick recap, root servers serve the root zone. The root zone sits at the top of the DNS hierarchy. This is the place of last resort, right? So if I'm querying for, say, umd.edu, if I don't know UMD, and if I don't know edu, I got to know the root. If I know nothing else but I know how to reach the root, then I can resolve a query. And so therefore, everybody needs to know, every resolver needs to know how to access one of the root servers, and the root server has to be available. So because it's such a critical part of the infrastructure, the root zone isn't hosted by one logical entity, it's hosted by 13 logical entities. And in fact, each one isn't just a single machine. Of course, we use IP Anycast. So as of the beginning of 2013, this was roughly the number of instances per root node. So as you can see, D here had 1, so we did not support Anycast at the time. So in order to support any IP Anycast, we had to change addresses. Oh, excuse me. There we go, right? So we had to move from Maryland /16 to a /24 that ICANN had provided. So in order to support this, we had to change IP addresses, but to help carry over, we maintain both the old and new addresses. So first, why is this a big deal that we're changing addresses? Well, first off, let's talk about how resolvers learn about this new address. There's basically 2 ways. The first is via some out-of-band mechanism. So for instance, in their hints file, they'll maintain the NS and A records for each of the different root servers. And in fact, many resolvers even hard code the addresses for the 13 root servers in the code. So when droot changed its address, sure enough, there were software patches to most resolvers. Now, once it's sort of initialized, it's sort of a bootstrapping phase. So long as a resolver can hit any of the root servers, they can also issue priming queries, which they do prior to the TTL running out. So there's a 6-day TTL for these root servers. And so they can also find out live what's going on. So University of Maryland, in order to help make sure that this transition went smoothly, started announcing just the new address, but still resolved queries to the old address. So in our experiments, we collected some sample set of the data. So on average, as we'll see, droot was getting about 15,000 queries per second. We captured samples of that traffic, and also so that we could pinpoint when exactly particular clients switched over from the old address to the new address, we also had some code running that looked at every single query and kept track of whether or not this was this particular IP address had switched over to the new one. So let's dig into the changeover a little bit. So we also have a little bit of preamble data, about a day and a half ahead of the change. And this was, so all traffic was going to the old address. And as you can see, it was about 15,000 queries per second. So what we would have expected, this is what we expected to see happen, okay? We're gonna start showing queries then from this day, both to the old address and to the new address. And what you might expect, if you take a step back and think about it, is that the queries to the old address might decrease over time, right? The queries to the new address would increase over time. And we expected that overall, the query volume would stay the same, right? If droot is a good server for you, all right, somebody's shaking their head, right? So in reality, what happens is that let's see what some annotations here, right? The queries to the new address picked up very, very quickly. The queries to the old address dropped off some, but kind of held off at this rate, and the overall query volume actually increased by almost 50%. And in fact, this wasn't just like a weird, well, we were kind of, figuring things out. So even, almost 4 months later, these same properties persisted. So we thought that, this is quite strange, right? So overall query volume has increased. Resolvers were still heavily, heavily using the old address. So we saw these things, and we said, what the heck is going on? And in fact, when we spoke to the droot operators, they said, oh, yeah, we were told to expect this. And in fact, looking at some of the old literature, somebody had written up about JRoot, and they found similar properties as well. But nobody really explained or why. Why was this happening? This is really, really strange. What's going on here? Another property that we happened to see also was that queries to the old address versus queries to the new address had very, very different failure rates. So what you really expect, so long as everybody's caching correctly, most of the queries to root should fail. These should be typos, weird things, right? You should be ideally caching most of the, if you have .com, you should be caching that, for example. So the real question is why? Why are these things happening? Why is there such a discrepancy in the failure rates? Why are we getting so much traffic to the old address? And why did the overall volume increase? So we'd seen these phenomena. Nobody had quite answered why. Today I'm going to show you why. We'll start off. This is also the outline of my talk, so I'm going to start off by discussing overall query volume increase. So to explain something like this, there's basically two potential reasons. Either there were resolvers coming to us who hadn't come to us before, or some resolvers who had been going to us before the changeover are suddenly issuing more traffic, or potentially both. It turned out, however, that we actually saw fewer resolvers than before. The number of resolvers coming to us did not increase. So the only remaining explanation was that there must be more queries coming from the set of resolvers who used to be going to us even the day before. So what we look at then is the queries per second per /24 on the day before, the 24 hours before the changeover, and then 24 hours after. Okay, so anybody who had no change in query volume would be right on this x equals y line, this 1x line, right? And we would have expected that everything would have been around this line, mod some variation of sampling and whatever the query volume might have been. So here's what we actually see. So these lines I'm showing you, so we have the 1x line, the 2x line, 10x, and 100x. So those above the 100x line are folks who issued 100 times more queries the day after the changeover than the day before. So we classify, and in fact, there's some folks who even send 10,000 times more queries to droot the day after, okay? So we classified these yellow dots here, anybody who had more than doubled volume when we changed over, as excitables. These were the clients, the resolvers that got very excited about the address change and really wanted to visit droot a lot. And in fact, these were exactly what account for the increase in volume. But still, there's the question of why? Why did they do this? So we did a little bit of detective work, and where do you start with detective work? Well, you dust for prints. So we tried FPDNS, fingerprinting some of these domains, and the thing is, most of these excitables, we weren't able to fingerprint them. That's our first piece of evidence. There's some resolvers that are kind of known not to not be supported by FPDNS, so that was sort of our first narrowed down a little bit. Additionally, the other piece of evidence was the spike query distribution. The fact that some folks suddenly just latched onto us and started issuing tons and tons of queries. And also this frequent repriming. So the fact that the new address, we thought, with TTLs of 6 days, that it would have, the new traffic to the new address would have slowly ramped up, but instead it just jumped up very quickly, which indicates that they're repriming much more quickly than maybe is strictly necessary. The final piece of evidence was that when we looked at where these queries were coming from, we saw a heavy concentration in Europe. So these things all together led us to believe that the issue is actually with a particular resolver, which is Power DNS. I'm seeing some head nods, so yeah. And in fact, so we were kind of curious about this. So one of this amazing undergrad in our lab set up an emulated network ran 13 root servers in this network, and then ran powered DNS, and then introduced a new root. And here's what happened. So this orange line here, if you can see this, was the client was set up running powered DNS version 3.5-1. The best root server for that particular client as set up in this emulated network was H, and then we added a new D root, just as before, which had latency of 85 milliseconds. So basically what it boiled down to, and we completely replicated, it switched over, it latched on completely to the new D root, even though it was by far not the best, almost 8 times worse latency. So it turns out that it has to do with, this undergrad then went, tracked down the bug, surprise, surprise, C++ template scariness, submitted a bug report. As far as I know, the ticket is still unfortunately open at this time. This undergrad is now a grad student and doing really good stuff. So to answer these questions, the first thing is we boiled down that the excitables, this increase in overall traffic volume could be explained by a bug in powered DNS. Now, what's going on with the old address, though? Why are we still seeing so much traffic to the old one? So the question is, who's going to it? We expected most folks to update correctly. We expect everybody to go from the old to the new. But in reality, what happened was that 63% of folks stuck with the old, 9% kind of swapped back and forth, and only 28% switched to the new and stuck with it. So we call the folks that stuck with the old as barnacles. They're just stuck onto the side of it, never switch over. And those who kind of can't make up their mind, we call them swappers. So what I'm going to talk about here, I'm going to talk about what happened with the barnacles. Happy to talk offline about what we think was going on with the swappers. What I want to dig into is what was going on. Why were some folks just stuck to the old address? So if you start looking at the types of queries they were issuing, then we see a couple different types on different ends of the spectrum. So some we see that are really random and always fail. These are just garbage queries right here, totally random things. Otherwise, sometimes what we see is we see very predictable ones that always succeed. Okay, so this gives us two features. The two features we look at are how diverse are the queries coming from these different resolvers, different IP addresses, and what is their failure rate. And it turns out if you use these as features, you plot these against one another, then a few things are going to fall out from this. So first of all, what would we expect when we look at failure rate versus query diversity? Well, ideally, it should be in the upper right-hand corner, okay? You should be failing most of the time because you should be caching and doing your negative caching correctly. At the same time, ideally, you have varying diversity. You're not just constantly asking, what's .cmo, what's .cmo, what's right? You should be in essence, I view the y-axis sort of is negative caching implemented correctly. I view the x-axis as is positive caching implemented correctly. We should be in the upper right-hand corner. So what we did first is to kind of sanity check these features. We picked a few normals, so some large ISPs that we expected to change over properly. And sure enough, they're really concentrated in the upper right-hand corner over here. There are some that are sort of distributed throughout. There were some instances where there were some ephemeral misconfigurations where we saw a ton, like this huge burst of queries to .internal. So clearly there was some internal private namespace that somehow ended up leaking out for a short period of time, but for the most part, they're in the upper right-hand corner there. Now what's going on with these barnacles, these folks that stick to the old address? Very, very different picture here. This is not matching the normals. What we see, the first thing to notice here is that the vast majority of them have very, very low failure rates, okay? This means that they keep issuing successful queries over and over and over again. So this captures, a lot of these are DNS blacklist checkers that just have this large list of domains and just keep checking a bunch of them. There are some who fit into this normal category, so they may be perfectly normal, say ISPs or different resolvers, who just happen not to reprime for whatever reason. Not really clear to us why. Additionally, we see a bunch of these barnacles who query from a very, very, very small set over and over and over. We believe these to be perhaps embedded devices or mechanized bots that are using the root server as a means of just checking to see if they have connectivity. That's our hypothesis there. So to answer these questions, we believe that both this latching onto the old address and the low failure rates to the old address can both be explained by these barnacles, which are results of misconfigurations, bugs, scanners, and so on. So this summarizes what happened with the changeover. I'd also like to propose something that might be a little radical, right? So in doing something like this, we switched over, we saw all these bugs, all these misconfigurations to this old address. Why not just do this every so often and use it as a periodic form of garbage collection? So the thing is, this IP address changeover is a historic event. See, this is university, so I can say weird out there things. But it really helped us identify lots of hosts that just are just introducing this, background radiation on the internet. And it was a really useful insight that unfortunately might be the last time we get it, because this was almost the last root server to switch over to Anycast. I want to tease a couple preliminary results. We started, now that droot has for about a year and a half, almost 2 years now, been Anycasted, I want to tease a couple of our ongoing questions. So with Anycast, with a couple new students, George Peterelli and Ming Chao Xiao, we're asking a couple extra questions. We're curious, how are hosts mapped to these different Anycast instances distributed across the world? Is it optimal in terms of latency? Well, it's not optimal. It's at least good, right? So if are my queries going to the other side of the world, or am I at least going to the one that's, if we're here, ideally we're hitting the instance that's in, say, Dulles. Also, interestingly, a lot of times attacks, say like amplification attacks, spoof the source address. But if we have many different locations throughout the world, you don't get a choice as to which of these different IP Anycast instances you get to go to. So if we could see higher attack traffic to some instances, we might actually be able to determine where the attacks are really coming from physically. So I want to tease one thing about this notion of how good is the latency that clients get to to the instance of droot that they're routed to. So this is one of the instances in Argentina, and this is actually really good. So the x-axis here is, I'm using distance, geographic distance, as a proxy for latency for the time being. But it's not exactly the same thing. Geographic distance, that in and of itself ignores water, but it's a reasonable proxy for the most part to get a sense of what's going on. And so ideally what we would see is that the distance between the optimal instance that they're going to, whichever one is closest versus one they're going to, should be 0. They should be going to the optimal one. So what we'd want is a straight line right at the y-axis. And for some hosts, we actually see this. So this is a host this is an Anycast instance in Argentina. The vast majority of the folks who are going to it, that is the closest one for them. So here's Dulles. Again, looks quite a bit different. I do want to point out that the x-axis goes up to 12,000 kilometers. So there are some folks who are going literally as far as they could get to IAD. So to show well, maybe that was the best one for them, here's a quick animation of who was going to IAD in the month of the month of May. So each of these regions here is the Voronoi region. So this is the geographic coordinates in these boxes these boxes each correspond to a different Anycast instance. If you're in that box, that Voronoi region, that Anycast instance is closest to you. So this purple box here is IAD, is Dulles. Anybody who's in that box should be going to Dulles, and ideally, anybody outside of that box isn't going to Dulles. There's somebody closer to them, geographically anyway. So here's the animation. What we see is IAD being a routing-centric area, a routing-centric part of the network, actually collects a lot more data or a lot more queries than it seems like it should. So to summarize overall, our Anycast analysis is ongoing, but it does seem, as initial results indicate, the Anycast does seem to favor routing-centric instances. If you're interested in more information, please follow us. There's more our papers and more information on this project website, and I'll be happy to take your questions. Hi.
Hi, Keith Mitchell, DNS Track. When you were measuring your IP address transition change for droot, did you compare the results you had with any previous root server IP address changes?
So we don't have data to that.
You do. Your OARC members, we have data on that.
Okay, awesome. I would love to compare head to head. Absolutely. So in terms of we looked at the overall dynamics, but in terms of digging into the data, let's please talk after.
Okay,
Let's
sure.
sync up. That'd be fantastic.
So Warren Kamari, Google. I probably just wasn't paying attention because I'm usually not paying attention. But can you explain why you had to change the IP address just because you enabled Anycast?
Oh, so to support IP Anycast, we need to be able to announce a prefix. droot was hosted inside of Maryland/16. I suppose maybe it could have been fragmented to, or we could have taken a /24 out of it, I imagine, but ICANN had given us a /24, so there's a decision amongst the droot operators to just use what ICANN had provided.
All right.
There might be like a much deeper reason for that I don't know, so I don't want to clarify, I'm not one of the droot operators, we worked with them, so I hope I'm not misrepresenting them.
Hi, Patrick Gilmore, Markley Group. Are you planning to shut off the old address anytime, and when?
My understanding is that it has been,
Oh, it
it has
has?
stopped responding to
All
queries.
right, thanks.
Yeah, but it stayed up for, I think, at least a year. If you have some ideas that I can relay, then I for one would love to keep hearing what's going on. Be fun.
Yes.
I'm suggesting garbage collection. The least we could do is, yeah.
So Michael from ESNet, one of the reasons you're seeing some perhaps not totally optimized Anycast routing is that in particularly the RNE networks will tend to favor RNE networks, which means that oftentimes when you have local pref set high, you're going to trump everything else, and you're going to send your traffic to an Anycast name server that's in an RNE network, even if it's in Japan, and you're not. So that sort of thing happens quite a bit, and we always sort of struggle to figure out what's the best way to local pref those things.
I see.
So the default way you're probably seeing a lot of, from the stuff in the west coast of the US going to IAD, you might actually be seeing a lot of internet too, and ESNet for that matter, clients going to droot.
Interesting. Yeah, there is sort of, this expectation that, IP Anycast will approximate, I guess. There's this tussle a bit, right? So there's policies in terms of what BGP gets you, which it doesn't guarantee anything close to shortest path or lowest latency, right? But then IP Anycast kind of, to an extent, relies on it. And the thing is that even if it doesn't achieve the optimal latency, it is still getting the resilience, which is really the primary, I think, one of the primary reasons for shifting to Anycast, for this kind of critical infrastructure. I'm sorry? I don't know. I'm sorry.
And no new V6 address?
I don't know either. Sorry.
Other questions? All right.
Thanks very much.
Sure. Warren, did you want to come up and? Yeah, let's, any other questions, or if not, thank you to all of the speakers, and thank you for coming.